Hello everybody! Today we're going to take a look at the binomial distribution. So, for a binomial distribution, the big difference between the distributions we looked at in the last lesson and the ones we're looking at moving forward is these are all based on pass or fail events. So the events themselves are pass or fail, and we're just going to look at sort of the number. The number we're going to look at is like the number of times we're successful. Okay, so first of all, for it to be a binomial distribution, all trials must be independent. Okay, and by that I mean that they can't affect each other. Every time I have a trial, the probability stays exactly the same. It's consistent. Nothing affects that trial other than the trial itself. Okay, we only have two possible outcomes. Okay. Success or failure. The probability of success is the same every trial. I already said all this. Okay. So the outcome of one trial does not affect the later trials. So the probability, and this is one of our more complicated equations, but the probability of being successful X number of times is going to be n choose X times p to the power of x times q to the power of n minus x. And that is where n is the total number of trials Okay, and p is the probability of success. And then finally, Q is the probability of failure. Okay. And of course, for these, P and Q should add up to 1 because we only have successes and failures. There's no third option. Okay. So the probability of being successful X number of times is going to be that there. Okay. So let's give it a whirl here. So we're going to tabulate and graph the probability distribution for number of heads in the tossing of a coin 5 times. So first of all, we have this chart here, so we can be successful 0 times, 1, 2, 3, 4, or 5 times. Okay. Obviously, because we're flipping a coin, let's just make a note here that P in this case is going to be 0.5. We have a 0.5 chance of being successful, and we would have a 0.5 chance of failure. Okay? So, we're going to have 5 choose 0. Okay, so there's 5 trials. We want to know the probability of being successful 0 times, so it's going to be 5 choose 0 times 0.5 to the power of 0 times 0.5 to the power of 5. Okay? And you can put it into a calculator if you don't trust me, but the answer is 0.03125. All right? And so we just go through and we do this for all of them. So we'll have 5 choose 1, 0.5 to the power of 1. So this exponent here, that one there, is going to increase by 1, whereas the exponent on the next probability, the probability of failure, is going to decrease by 1. Okay. Yeah. So, and that makes sense because we're having 1 more success and 1 less failure. So again, you put it in your calculator if you don't believe me, but it is 0.15625. All right. And then we just go again. And so actually, before I move on, so like I say, I mean, what this one represents here is that is us being successful, which in this case, we wanted it to happen once. This is us being unsuccessful or failure, and it happening 4 times. And then this here is just saying, well, it can happen in any order. We could have that 1 success first, or it could be second, and so on. Okay, so that's where those numbers come from. You don't necessarily need to know that, although it can be helpful in more complex questions. So anyway, so we just keep going. We got 5 choose 2, 0.5 to the power of 2, 0.5 to the power of 3. Remember that those exponents must always add up to the number of trials. If they don't, then you have made a mistake. So we got 0.132 or 3125. Okay, and then we'll have, that's a 2 right there, by the way. So then we got 5 choose 3. So we've got 0.5 to the power of 3, 0.5 to the power of 2 equals, and this one will also be 0.3125. Okay. And then we have 5 choose 4, 0.5 to the power of 4, 0.5 to the power of 1 equals 0.15625. And then finally, we have 5 choose 5, 0.5 to the power of 5, 0.5 to the power of 1, and that is equal to 0.03125. Okay? So if we were to graph this, which we are going to graph, and remember, as I said in the previous day's video, I won't actually ever make you graph this on a test. It's just more so you can see how this looks. So I had, hold on, let me space that out a little bit better. So we'll go 0.1, 0.2, and obviously I'm just sketching here because this is really inaccurate, but 0.4 and 0.5. So our dots are going to be, we'll have one quite small right here, and if you look, the one on this side was exactly the same, and then we had one about here and here, and then we would have one about here and about here. So it's a rough sketch. So anyway, so that would be 0, 1, 2, 3, 4, and 5. And you can see it's symmetrical in this case. It's completely symmetrical depending on how many times you'll be successful. And that makes perfect sense in this situation because the chances of being successful are the same as the chances of being unsuccessful. Okay, because you're just as we could easily make this question about succeeding by getting heads and all the numbers would be exactly the same. Okay, and so that's why it's like that. It will only be symmetrical like that in the event that it is a 50-50 thing where the chances are the same. Okay? Expectations. So the question here is, what do we expect? And so, in other words, how many times do we expect to be successful? And so this one's a much more simple equation than the last one. You just take the number of trials and you multiply it by your probability of success, and that will give you how many times we expect to be successful. Okay? And that's it. All right, so let's take a look at another question here. So, Jamie's family moves to an area with a different telephone exchange, so they have to get a new phone number. Numbers in the new exchange start with 446, and all combinations for the 4 remaining digits are equally likely. So, her favorite numbers are the prime numbers 2, 3, 5, and 7. We're going to calculate the probability distribution, first of all, for the number of these prime digits for her new phone number. Okay, so the first thing we need to do here is you want to go through and you want to define your N, your P, and your Q, okay? Or not define, sort of figure out what they are, okay? So N here is number of trials. So we're talking about choosing a 4-digit phone number, okay? So there's just 4 trials. She's going to choose a number 4 separate times, okay? So your N is 4, okay? Our P, our probability of success, well, there were 4 numbers that Jamie liked, and that's out of the 10 possible digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, she only liked the 4 prime numbers. Okay, it's worth noting that you could reduce this, but usually in these cases, it's actually easier to just rewrite it as 0.4. Okay, and then the probability of success, how you figure this one out, the Q, is up to you. You could just say, well, there's 6 numbers she doesn't like out of 10, which is 0.6. Or if it was more complicated numbers, often the easiest way to figure this one out is to say what's 1 minus whatever that probability of success was. Because If we're not successful, we're unsuccessful, and you'll get the same numbers. And obviously the math was fairly simple for this one, but if it's a complicated one, it is a nice little trick to have. So what we're going to do is we're going to make our chart here. So we're going to say 0, 1, 2, 3, 4. So when you're doing these, don't forget the 0. A lot of times people forget to put the 0 in there, and it throws the rest of the numbers off. Okay? And then we'll do the probability of success. So we're going to have 4 choose, I'm going to zoom in even further here. 4 choose 0 times 0.4 to the power of 0 times 0.6 to the power of 4. And then we've got 4 choose 2. I'm just going to fill it all in like this. Save myself some time. So we got 0.4, 0.4, 0.4. Okay, and then we can just go 1, 2. I missed one. Oh man, let's try that again. What did I miss? Oh, I missed the 1, that's why. All right. Well, I tried to make it easier and I blew it. Hold on. Try that again. I didn't even erase it well. There we go. All right. This time we'll get it for sure. So 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. We got 0.4 to the 1, 0.4 to the 2, 0.4 to the 3, 0.4 to the 4. And again, it makes sense that it's going up because it's just saying that number is increasing. The number of times we're being successful is increasing. All right, 4, 3, 2, 1, 0. There we go. All right, and you can put them into your calculator yourself again. If you don't believe me, which at the rate I'm going, I would understand, but here we go. So it'd be 0.11296, 0.3456, 0.3456, 0.1536, and finally 0.256. Oh, I missed a 0, 0.0256. There we go. All right, so that's all our probabilities. If we were to graph that, you can see this in this case, I'm just going to do a really rough graph here, but you can see it would be, it's not symmetric this time, okay? These guys right here are the same, but there's only one thing here, and then it's kind of trails off here. Call that right skewed, okay? So anyway, so that's what I mean whenever I say calculate the probability distribution. I just want you to find the probability of all the different possibilities, okay? And I won't give you an incredibly difficult one if I'm making you do them all. When I'm making you do an incredibly difficult one, you'll only have to find 1 or 2 or a couple anyway. All right, so how many times do we expect her, how many digits do we expect her to get that she likes? So this is our E of X. I don't even remember switching to blue, but here we go. And we just say, well, she's got 4 trials, okay? Each time she has a 4 out of 10 possibility of success. So that's going to give us 1.6. So she expects to get 1.6 numbers that she likes. And of course, as usual, that doesn't make any sense, but that's okay. It doesn't have to make sense because expected value is not it is just a theoretical value. It's not a real thing, okay? So she expects to get 1.6, okay? All right. Your counting candies question here is what we're going to do to start tomorrow's class. So that's it for today. Until next time, go Sabres.